Thanks very much for the invitation from the organisers. It's really wonderful to be here. I'm going to tell you a little bit about object data analysis, and primarily through 3 applications where I'll illustrate some of the ideas that are going on. So the plan for the talk is the following. First, a little bit of introduction. Then I've got 3 applications I'm going to talk about. One to do with DNA variability, one to do with arteries, and another to do with enzymes. And the 3 applications are such that you don't have to get too worried as we go through the first one, because the first one is longer in terms of time than the second one, which is longer in terms of time than the third one. So don't get too worried if it seems to be going slowly. The second 2 are shorter than the first one. Right, so we really do seem to be in a new era. So data seems to have had this enormous amount of interest, which I've never known before, how topical the fact that data is really everywhere. Everybody wants to analyse data, and we seem to be in this new era, as this quote here from Jeannie Rometty, Chairman, President and CEO of IBM. So you can read it yourself. What steam was to the 18th century, electricity to the 19th, hydrocarbons to the 20th, data will be to the 21st century. And it really does seem as though there's a lot of truth in this. So data is a new natural resource. Now, I would say what's new about data? Data's been around for a very long time. So here's a reasonably topical picture here. So, very nice graph that I noticed last year in The Economist, looking at the onset of spring, and it's just amazing how old this data actually is. When you look at the first date here, 800 is the year of the first data points, and collected the date of the first cherry blossom in Kyoto, Japan. And it's remarkable that this has been recorded, and I think this picture illustrates what I would want to be doing with my applications, in nicely plotting some data, and the data tell you the story of what's going on here. So can anybody tell me what you think's going on here? Offer me some suggestions. What do you think?
Climate change.
Looks like there could be some possible evidence of climate change here. Some sort of smooth line has been plotted through here, and some nice intervals that illustrating the uncertainty of the estimate. And it really does look as though, from at least this estimate, as though it's coming in a bit in time. So the cherry blossom peak bloom is a bit earlier recently than before, and we've got nice error bars here to help us to decide that that is important and actually significant. So I also like this picture because it's got nice cherry blossom petals as the data point, so that's also a very positive feature of the data. Okay, so this is what I want to do with my data sets. I want to illustrate clearly what's going on, so that I can report back and discuss with my collaborators. Now, if we look at the traditional types of data, then in our beginning statistics courses, we tell people that there are count data, 0, 1, 2, etc. We can measure continuous measurements, and we might have lots of measurements, but these really only cover it certainly covers a lot, but it doesn't cover all the types of data that we come across. So in this workshop, we've already seen many complicated, structured data. We've seen faces, we've seen covariance structure, we've seen like speech analysis, and very complicated, highly structured types of data, and many others besides. So the subject of object data analysis has perhaps really been around probably for, at least in terms of this name, for a decade. Steve Marin has been talking about this a lot and really coined most of the phrases, where what's of interest is not just numbers, counts, but an object itself. So Steve always says that the first thing to ask when you're faced with a problem is, what are the atoms of the data? What are the actual things that you're going to be studying, and what's the important basic structural element of your data? So in, I think it was 2010-11, we organised a program with Jim Ramsey and Hans Muller, Jane Wang, Steve and me, where we were looking at lots of ideas and exciting ideas to do with object data analysis. So the themes were of that particular workshop were looking at things like functional data analysis, dynamic systems, shapes and manifolds, which is the area that I've perhaps done most work myself personally, images, and really very unusually structured data like trees and graphs and networks, and these are all the sort of things that you want to do in object data analysis. So the common thing in many of them is that the data live on some form of manifold. So this is as technical as it will get with regard to manifolds. Manifolds are, as we heard in other talks, they have a geometrical structure. They can be flat. So if you want to go or walk from a point here to a point here in a flat space, in the shortest route will be to walk in a straight line. If you have some curvature in your space, so you have a curved manifold, saying you want to walk from here to here, it may not be the shortest route to go in a straight line, and there may be all sorts of reasons why it's not a good idea to go in a straight line there. It's slightly shorter to go around there. So on manifolds, you're not talking about just straight line distances. You'll need a different way of measuring the distance. So you need a metric is the basic quantity of interest in order to decide how far apart two points are, and then you will need quite a bit of extra geometry that goes with it in terms of describing the local structure, the curvature at each point in the space, and how you actually move around in the space. So we're going to be dealing with manifolds, and one of the common themes as well is dimension reduction. So there are lots of different ways of reducing dimension, but PCA is a very common workhorse that does well in many applications, and we're going to be using that here as well as other things. So you've got something in high dimensions. You want to find the sort of center of your data, and then you want to find the axis that describes the most variability, and then orthogonal to that, the axis which describes the next direction of variability, and then project into this lower space. So we're going to make use of PCA as well. Okay, so here are my three applications, and the first one is about DNA. So this came from a application where colleagues in pharmacy, so we have a school of pharmacy at Nottingham, and they are interested in studying the way that drugs, for example, have an effect on the human body, and one particular group is interested in the damage to DNA. Every time we go outside and the sun's shining, thousands of bits of DNA get damaged, and then miraculously we don't just fall apart, we manage to repair that damage. And some of the stories they tell, it's remarkable that one actually managed to survive the day. But we all do, and because the human body is so wonderful that there are lots of amazing things going on. In particular, they're interested in describing how DNA repairs itself after it's been damaged in particular situations. So this data came from molecular dynamic simulations. So it's actually simulated data, but this is often how they work. They have, in particular, there are 22 landmarks, which are phosphorus atoms on DNA. Hopefully you can see the rough sort of helix shape here of the DNA. And they simulate it over time, and very, very short periods of time, picoseconds, so 2,500 picoseconds of time, and they want to observe how the DNA is changing after it has been damaged. So just to give an example, we have a string of nucleic acids along the DNA, and the middle three here, in this case TGC, what happens with the damage is that one of them, the middle G here, gets changed into something else. So the guanine nucleic acid gets changed into something else. Just call it letter G goes to F basically on one of the DNA sides of the DNA, and then how after that has happened does the DNA change shape and its variability. So it's moving over time, and I'll just show you a quick movie of the sort of thing that you'll see. Right, so hopefully this will work. Right, so let's just give you an idea of what these simulations are doing. So you've got the DNA, and you've got it in a box of water molecules, and so the water molecules can all move around, and it's actually generated just by using Newtonian mechanics. At each point in time, you work out where all the atoms are going to be, and this is just displaying the phosphorus atoms. There's all the water molecules and other atoms as well. So we want to be able to describe the shape change and the change in variability after one of the atoms is replaced, or one of the nucleic acids, sorry, is replaced in the middle from a G to what's deemed a letter F. Now the actual summarizing the variability can be done using principal components. So we've got all this data. We're not interested in the location of the molecule or its rotation. You know, it sort of rotates round. So we can get rid of that by doing the Procrustes analysis, which we've heard about from Victor and David and others, where we will basically register all the data so that you can get a common mean, and then once you've got everything into sort of common registration, you can project into a tangent space to the shape space, and then do PCA there to look at the main directions of variability. So here's an example where I'm going to just show the main structure that's picked up in the first principal component. So it basically gets rid of a lot of the noise and describes the main structure. It's not always easy to explain exactly what's happening here, but this is essentially basically some form of twist going on with the DNA. And then another principal component is bending. So, oh, right, wrong one. So that sort of looks a bit more like some bending. So you can summarize the variability in a reasonably low number of dimensions for something like the DNA with sort of twisting, bending. You get a few principal component scores, which are then describing what's going on. Okay, so if we go back to the right. Right, so the 6 groups are given here. Probably the detail doesn't matter so much, but there are 6 groups where the middle 3 letters are different, depending whether it's encoding for different amino acids, cysteine, arginine, serine, or TGA just is a stop codon, so it doesn't code for anything. But we want to see whether when we have damage, the DNA is different when it's not damaged from when it's damaged in each of these 6 cases. So if I go forward and here's another view of the data, just sort of a side view, and then looking down the DNA here. I've just joined with lines up through all the data points, but you can see the celic shape, celic helix shape there. So this is described in this paper here with Charlie Lawton is the pharmacist who we're working with. Now, I want to describe the mean and the variability. So it's the variability in particular that the pharmacist feels is very important. Not just that it changes shape, but the way it varies is thought to be important. So going back to the example we've seen in other talks, and starting off right at the beginning with Victor, if we have a space of m by m symmetric positive definite matrices, so this describes the variability. A covariance matrix lies in this space. We will have a covariance matrix of size and shape for DNA. And we want to see if the covariance matrix is different when it's damaged than when it's not damaged. And also we want to see if the mean is different when it's damaged or not damaged. So here's a diffusion tensor image where you have little covariance structures at each point. So Rainer von Sachs had pictures just like this, where it's of interest to look at covariance matrices or diffusion tensors at points in space. And in order to do analysis, one often will want to use a different metric from the usual Euclidean metric. Okay, so some brief notation. So transformations, it's often good when you're looking at distances to either work on a square root scale or a log scale. So if I've got my covariance matrix S, then if I want to take the square root, I could use the matrix square root, which is just doing spectral decomposition and then square root in the eigenvalues, or I could use the Cholesky. And as David pointed out this morning, it's not unique. I can use lots of different sorts of square root, and I can put any rotation reflection here, and that will do. So that's used in the Procrustes metric. Or a matrix logarithm, then I take the logarithm of each of the eigenvalues, and that gives me the matrix logarithm, and that's used in metrics as well, although you better be certain that there's no zeros around before you try and take logs. So that one requires that you really do have positive definite. These ones, well, certainly with the square root, you can have some zero eigenvalues. So there's a long list of metrics for covariance matrices. These are only probably some of them, but here's a list here, and what we're going to do is investigate for the DNA how the variability changes using these different metrics, and whether we see a similar pattern or not. So the Euclidean is the one that most people are familiar with. We've already heard about, I think, most of these already, but maybe not all of them. But the log Euclidean Riemannian are very, very similar. The Cholesky is just the difference between the Cholesky decomposition, the root Euclidean here, and then the Procrustes allows you to rotate to get that sort of optimal square root as well. And then you can normalize, that's another one, or choose different powers, not just half. And then the computation of the geodesics between different objects is available in all these cases. So they're very simple for things like the Euclidean and Cholesky, log Euclidean. The Procrustes, after you've done this matching, it's straightforward. The Riemannian metric requires a numerical algorithm, so some sort of gradient descent to find the average along the path, and they're all available in this package here, the shapes package in R. Okay, and the properties are quite different. So the Cholesky one isn't really great, because if you were to rotate the to both S1 and S2, then the distance changes, so that's not very good. If you scale, then the Riemannian log Euclidean and this full shape similarity one are invariant, and the Riemannian one is also affine invariant, so that's a nice property too. but you can't use it for rank deficient matrices. And as also has been pointed out by others, there's this swelling that you get with the Euclidean that you don't get with some of the others. Right, so you can sort of see the effect of these metrics. If we had on this side, I've got one covariance matrix which has a very strong direction and fairly small variability in the other parts. And then here is another one, and I want to interpolate, walk along the geodesic from one to the other. The first one is the Euclidean one, so you can see it all goes very big in the middle, so this is the swelling effect. This is the Cholesky here, which does that. This is the Procrustes one, the Siam one here, and this is the log Euclidean Riemannian one. So they often actually shrink a bit in the middle, I've noticed as well. So this one swells and this one shrinks a bit. So Procrustes one sort of has a bit of a balance between the two. And there's just another example which really illustrates the swelling of the Euclidean. Going from there to there, it goes through that path on the way, which is really not good at all. This one, you can see the shrinking a bit with the log Euclidean versus the size and shape Procrustes one. Okay, so we need to go back to the DNA. So I've got any of these metrics will be appropriate for describing the change in variability. What I've got here is a canonical variate analysis plot. So it's basically like PCA, but taking into account the group membership as well. So that's probably not fair to call it exactly like that, but it's along those lines. And so it does a low dimensional projection and best separates the groups as well. And then, although it's a bit small here, you can see that the damaged are in blue, and the damaged are in red and the undamaged are in blue, and you get quite different behavior in the different groups. So this one here, there isn't a huge amount of difference between the undamaged and damaged, and as you go down here, it gets a bit bigger. It's a very big difference here, and then a bit of a difference here. So we want to see, what are the whether these. Well, you can see that some are clearly going to be significantly different in the mean, but is the variability significant as well? So that gives you a hint of what we'll see. There's the changes, just the changes in the mean on the same plot. So one of the groups, this AGC, which I think it should be, AGC, and is a huge difference there. The AGA and the AGG, that should say there, are fairly small differences, and the TGC is also fairly small, that blue one there. Right, so if we want to test for a mean difference, then you've got a fairly large amount of parameters, and so we considered a factored model with using the rows and columns Kronecker product here, which at least reduces the amount of parameters that you've got to estimate. And it's also a time series which is very strongly correlated. So we've done some thinning of the time series at different levels of thinning in order to be able to assess whether the mean is different or not. So this one is thinned so that every 100th one is used. This one is so that every 50th is used, and this one so that every 25 is used. And you can see that there's less change in the groups AGA and AGG, which encode this particular nucleic acid, arginine, and the TGC for the cysteine. So if you, it's one of these things where there's a bit of an ad hoc choice. If I thin at a certain level, I see that that nothing much is significant. If I thin at a medium level, then you can see which ones are closest, and some are definitely different. And then if I keep going, because I've got so much data, everything's significant, which is the usual problem that you have with any sort of big data set, that everything's significant. So this gives you a guide as to which ones are more significant than others. And then looking at the covariance difference, this is just a simulation study just to see which of the metrics was sort of best when you had multivariate normal data. They all perform fairly similarly, actually, in this particular case. So we did it when we had no correlation, when we had a strong correlation. For normal data, the highest power was the Riemannian and log Euclidean. The Procrustes one was in the middle, and the Cholesky and Euclidean were not quite so good, but they're not very different. They're fairly similar. One of the things that the Riemannian one is actually almost identical to the standard boxes M likelihood ratio test for testing differences between covariance matrices, which was an interesting thing that came out of this. Although, I mean, it may be well known, but we hadn't seen it before, but they're almost identical, and you sort of linearly related the two statistics. Okay, so for the DNA data, then looking at the covariance matrix difference, we can run a permutation test based on the statistics looking at the differences between the looking at the distances between the two groups, covariance matrices. So there's a whole raft here of the different statistics we use. That's the Riemannian one, Procrustes with scaling, Cholesky Euclidean, log Euclidean, and the boxes M is the one which is the maximum likelihood one that you would do, which is very close to Riemannian. And at the end of the day, there was no change in variability for this first group, this AGA group, and the TGT group, whereas there was for the rest. So there is a sort of a, it's important to see whether this means anything. From a pharmacist point of view, the important thing is that damage to this base in DNA for these particular types of DNA where you have AGA and TGT in the middle, which encode for these, would be harder for a repair system to spot. So because the variability is similar, whatever's repairing it won't be able to spot it so easily as in the other cases. So that's the biological thing. Conclusion. So any questions at this point? Yeah?
One question I had is, do you care about the dynamics as well, or just about, so do you care about lag zero covariance only, or perhaps different lags as well? Could that be of interest?
Yeah, so it is of some potential interest, but they all have very, very similar dynamics. They're all roughly looking like autoregressive type dynamics. Yeah, so it's not the main feature here. It's sort of what the lag zero variability is that's most important. So it's not like one is sort of much smoother moving than the other, and the other one is. So they're actually quite similar. So yeah, you do need to look at that as well, and I haven't displayed that here. But
maybe if I can also make a comment, because
yeah.
I looked at a very similar problem,
yes.
And I know the problem of having a lot of data, and it's not clear what a lot really means because of the very fine-grained temporal resolution.
Yes, yeah.
But one thing we did to decide whether or not differences really exist or not is actually look within the same time series, look at two periods that are sufficiently far apart.
Oh, yeah.
You expect that the characteristics are now the same, and you see
yes.
at what length do you start rejecting when you know, in fact, that things should be the same, and that maybe gives you some characteristic scale beyond which
yes.
you shouldn't be going to test your hypothesis.
Yeah, no, that's a good suggestion. Yeah. Good. Right. Any more?
Well,
yeah.
An observation that, because this often comes up, how things change over time.
Yeah.
But oftentimes, long-range correlations that seem mysterious can be easily explained by certain covariates that can be brought in as collateral information, such as Michelle was mentioning in her talk. And one test that I sort of carry around in my mind as a test of the maturity of any methodology is its capacity to bring in that collateral information from other sources in order to explain what's going on.
Right. Yeah.
So far, maybe in this covariance world, I haven't seen much of that.
No.
That may be something to keep your eyes on for future development.
Yeah. Good comment. Yeah.
For example, principal components analysis is very closely related to partial least squares. That's not a well-known fact, but it is the case. So, for example, partial least squares provides a more or less continuous map between a principal components estimate of a low-dimensional basis and a low-dimensional basis that best predicts one or more external variables. And that would be an interesting way to modify this kind of technology.
Yeah, no, definitely. Yeah. Good. Any more? Yeah.
So do you have a feel for how sensitive these guys are to the sort of types of alternatives? Because the fact that the Euclidean didn't do well actually doesn't surprise me. But it's only going to do well with these sort of really big overall changes. Where if you have things which are much more local, it seems like you have to go to something else.
I think it very much does depend on what's being picked up, and it would depend on the model underlying it. So in this particular case, in retrospect, it may have perhaps been obvious, but it wasn't until we saw it that under the particular multivariate normal model, the Riemannian one was the best. And so it depends on the model and it depends on the situation. And often looking at a large range of different models and real data sets, you get a feel for which ones do well and which ones don't. And I quite like the Procrustes one, which Victor spoke about, but because it sort of has a balance between sort of being very, very normally based and very, you've got to be away from low rank covariance matrices, which is the Riemannian one, and then the Euclidean one, which has these other problems which you can are well documented. So it sort of seems to do quite well. But yeah, it does depend on both on the alternative and what the models are. Right, I promised you the second two are quicker, so don't worry about that. Yeah, so we've got 20 minutes left, and we'll see how we go. I was going to warn you in advance. There's a medical diagram coming up, but it's too late now. It's not a real photograph, but I can't personally. I don't like it when you're in a talk and somebody puts some, insides of somebody in the middle of an operation. It's just awful. And this isn't quite as bad, but it's just that. But still, some people might not like it. I don't really like looking at it myself. But anyway, so this is actually from the same group that you mentioned in your talk, the MOX group at Milan, where they're interested in the carotid artery. So the internal carotid artery, and looking at the shape of the internal carotid artery here, so this bit here with the twist up there, and in particular they had data when there was an aneurysm. So these are all the actual data. So there was an aneurysm higher up than this part of the carotid artery, and that in some patients it was very high up, an upper aneurysm, and in some it was lower down, a lower one, and then there was no aneurysm. And the really dangerous ones are the upper aneurysm ones, and so it was of interest to see if the curves of the internal carotid artery are actually different for these different groups. So 6 groups. One is whether you have a left-handed, or 3 of them are whether they're left-handed, and 3 whether they're right-handed. And the upper aneurysm, lower aneurysm in red, no aneurysm in green. So these are sort of left-handed ones, and the right-handed ones here, the blue, the cyan, and the pink. So we wanted to be able to describe the difference between these. So this data very different from the previous one in that there are there's no obvious landmarks here like there were for the phosphorus atoms in the DNA. They're basically curves in 3D, but they do have some common structure. So it's of interest to be able to describe the shape in the groups and to be able to say what's different about the groups. So they're different lengths, these arteries. So you've got to think, how are you going to register them? And we're going to consider translation and rotation in 3D, and then a shift in the abscissa, which is the point in which you start recording the point. So there's points along the artery at about roughly, I think there's a roughly 1 centimetre apart. Well, I can't remember exactly, but anyway, it was regularly spaced. So we don't want to stretch them, we want to keep the scale, but we might want to start counting at a different place. Okay, so if you've got two arteries, so the red ones here are two different individuals, and I want to compare them, just like in the picture where I had my map at plane and mountain at the beginning. I want to be able to say how far apart they are. I want to be able to measure the distance between these two, and there's lots of choices I can make. But one thing we have done here, at least, is weighted Procrustes analysis. So there are different lengths, these two arteries. So we've made them the same length by extending them at the end, just shooting off in a straight line at the end here to give them extra length. And then we've done this Procrustes analysis. We've minimized the squares between the two and allowed for a change in the abscissa where you start and stop, and then the extra bit at the end has had like 0 weight, so because it's just fake data at the end, so it's just had 0 weight, and you can register them using this. So all of them can be registered to each other. Here are the two registered ones here, and then the distance between these two could be, for example, just the square root of the sum of squares distances of all the points, which is just the Euclidean distances after you've registered. So you can get a distance, and that's like a Procrustes distance between the two arteries. And this is what happens when you put all the data together and reflect the left-handed and right-handed ones together, so that that's not important. We just want to see what the shape is of them when they're being reflected. So that's all the data, and I want to be able to describe the difference in the 6 groups. So here are the 6 groups after they've all been registered. So the black and the blue are the dangerous ones, the upper left and right, and then these are the lower ones, not so dangerous, and these, the green and purple, no aneurysm, so not dangerous at all. I want to describe the difference in shapes in these. There's not much data in the no aneurysm, so it's a bit harder to compare those. So if we look at the group means of the groups, so we've got the so the black one is the upper left, red one lower left, and the green one no aneurysm. So if you look at these, so there's the left and the right, you might be able to see they seem a bit more twisted, the green and the purple one, a bit more bending going on. It's a bit hard to see though, so if you actually line them up a bit, first of all we'll look at the torsion. That's how much they lie in a plane. So if you've got a 3D curve and it lies in a plane, it will have no torsion. If it comes out of the plane, then it will have either positive or negative torsion. And then the curvature, how wiggly it is as well, can measure the curve. So you can see that the black and the blue, which are the dangerous ones, seem to have less torsion than the other groups. So they're a bit flatter around here, and they also seem to have possibly less curvature and then the purple and the green, where no aneurysm, have got much more torsion and much more curvature here. And when you look at them, I mean, you can stare at these and come up with all sorts of reasons for why they're different, which is a dangerous thing to do. But I think given the previous picture, it does look like the black and the blue are less curved and less twisted than, for example, the pink and the green, which come out of the plane more, and there does seem to be a difference. And the ones which are more dangerous, which are less curvature, less twisted, are the dangerous ones, and the blood is flying along through these arteries, so it helps to have some twists and curves to slow the blood down a bit rather than a straight one, which could be, well, at least that's what's in the upper aneurysm one, when they're a bit straighter and the blood will be flowing faster through them. So it's not that convincing a test. We did a test for difference between the upper and lower groups. I mean, there's some sort of weak significance, but it gives some possible explanation of the differences between these curves. Any questions on that one? I'm really going to go very quickly through the last one, don't worry. So, okay? Okay.
So your interpretation is basically that when the clot starts moving, if you have more twists, it's more likely to sort of stop it. Is this
basically, yes. So it seems better to have sort of a twisty, turning one. And so,
any cardiologists, if they...
Well, we with the people who we work with on the data, the MOX group, who one of them is very works at Emory University, and they we had a workshop at MBI, didn't we? And we all lots of us analysed this data in groups, and so there was a proper expert there as well as the amateurs involved too, and the feedback was that this seemed reasonable.
As I recollect it, the twists play a very important anatomical role. They are shock absorbers, because when the heart pulses, it produces a pulse. It's extremely high. It's a very high pressure pulse, and so the effect of these twists is in effect to absorb the shock by essentially transmitting it to the soft tissue around the artery, and those arteries which don't have that capacity are more likely to fail as a consequence. Which is another way of saying that the dynamics in these data is actually really important.
Yes.
And that as object data, I think ultimately we have to think of the dynamics in the same.
No, absolutely. And the study you mentioned in your talk was looking at the flow and the other side. So that group worked a lot on it, and shape is one part of it, but the dynamics and fluid flow are very important too. So it matched up with the general story.
Since you did mention about constraints and so on, did you take into account that curvature is also constrained as a function and in some sense cannot vary arbitrarily? Could this be important in terms of how it can vary?
So what do you mean? Sorry.
So I mean, if you think about it as the inverse of an approximating circle at some location, then you have some non-negativity constraints.
Yes.
And so on.
I mean, in this
depending how you define it, right?
Yeah.
Various definitions you could give, but
in this case, no. I mean, it was just treated as a function. So you can't just sort of go off too far or anything, but it was just how they compared relatively to each other. We were looking at, but. Yes, there is that extra information.
I was wondering if it might. I don't know. It was neutral as
well. It could. I mean, it's not something we considered, but it could be something useful. Right. Okay. Final bit. This really is very quick. This one, I promise you. So the enzymes, in some way, are a bit like the DNA, but these are a little sort of catalyst molecules that have an enormous range of shape variability. So here is again over time, but a few equally spaced points in time, one particular enzyme going through all sorts of contortions as it evolves through time. And what's of interest in this application is to cluster the enzyme into different states, so that you could say that it's in one particular state for this time, and then it might take another state, and then it might take another state. So it's clustering of shapes that's of interest here. And so if you look over time at this particular enzyme evolving over time, then the size of it, which is simply a centroid size, just a standard measure of size, is plotted here. So it starts off in a rather artificial situation which is very large, and then it settles down, and then it goes through a couple of periods where it seems to have a different size for a while. So if you just look at the size of it, it seems to get smaller in a couple of positions. And we want to be able to look at how the shape changes as well in this time. So PCA could be used as one particular method. So these are just the first two PCs, and those are regions that are had in grey and orange on the previous one when it got small, given here, so fairly near the edge. And we also used another method called principal nested spheres, which is a bit different from PCA in that rather than looking at lower dimensional Euclidean spaces, which PCA does, is to look at successive lower dimensional spheres that you fit to the data. And the details are not important for here, but you get rather different plots from PCA. So this is a P&S plot here. It's different from PCA, and it helps to pull out clusters. I've clustered here with 4 clusters, orange, and it wraps round on this axis, so it has a sort of circular axis here. Green is that's one cluster, blue and red. And when you actually look at over time, here, this middle one here is the cluster through time. The sort of green bit and the red bit are those times when it went small, and the blue and orange are fairly similar to each other. And then when you look at the actual shapes, then you can plot them in the cluster. So there's a period when the orange and green were very different from the others. So, and this one as well. So you've got this shape when it goes very small, and when it's in between here, the cluster 4. Okay, so that's another application. So 3 very different applications. Well, the last one sort of looks a bit like the DNA, but it is quite different. And it gives you just a flavour of what object data analysis is about. All of them, you need to know what your data are. All of them, there's a manifold involved in all these 3, so you've got to make a choice of metric, and hopefully you'll get something out of it which is as good as looking at that cherry blossom plot. Maybe not quite so nice, but this is a nice plot to say that different states of the molecule enzyme as you're going through. Okay, so I've hopefully told you about this a little bit more about object data analysis, the new area. We certainly need a lot more, though. I feel as though we've only just started, despite the fact sort of Steve started it 10 years ago. We need more methods, certainly more models. There's not so much in the way of models, and better ways of measuring uncertainty, I think, is needed as well, rather than just resorting to permutation tests and bootstrap. I think we need to be able to quantify the uncertainty in a better way than that. So this is one of the things going forward. So I'd just like to thank my co-authors. So most of the co-authors have at some point in time passed through Nottingham or South Carolina. So the first, David Hitchcock's at the University of South Carolina, and Wen Cheng, Blake Hill were there as well, and Hao Wang was there, and my other colleagues here have all been at Nottingham, and they're the sponsors, and then the final references are there. So thanks very much.
Okay, thank you. Do you have questions?
Yeah.
So maybe a bit about the first application, about the positive definite matrix. You mentioned a bit the advantages of like different metrics, but to me one big advantage of the Riemann and the log Euclidean metric is that if you take a space of positive definite matrix, equip with this metric, then it is like a geodesically complete manifold. So it's like a complete metric space. You can extend geodesic curves indefinitely, which is not the case for the Euclidean metric, but for the Procrustes metric, can you say something about this, or?
So with the Procrustes metric, the boundary is not it's a finite distance to the boundary. So you can have objects lying on the boundary. They're not infinitely far away, but Is that such a big deal? I don't know.
Well, so I think if you want to show some asymptotic properties of estimators
Oh,
under
yes.
certain metrics,
Yeah.
then this is pretty nice property to have. I think.
Yeah. So it's true that if you wanted to do things like a central limit theorem around a something on the boundary, you'd have to be very careful. You want it inside the boundary for any sort of result like that to work. But you can't do it on for those either, can you? Because they'd be infinitely far away.
So I know that for the Riemannian metric there are central limit theorems existing for. So, I mean,
Yeah.
I use this property quite often in proofs, so that's why I have problems with other metrics because I don't
Okay.
really have this property.
Yeah. Yeah. No. I mean, this is an advantage of the Riemannian and the log Euclidean. I agree. The log Euclidean is wonderfully simple to compute. You just take logs and add everything up and divide by n, and there's your mean. So, there's a lot to be said for that as well. So. And the Procrustes isn't much more difficult than that either. Yeah.
Do you want to say something in these problems about the issue of registration versus like follow-up statistical analysis, or how do we separate this, or is there any way of quantifying the effect of registration on the statistical?
Yes, there is. So, you have you have several choices, but a couple of choices are, in these examples, we've optimized over registration. So we've found the best registration and then done everything sort of conditional on that. Another way is to model the registration and then perhaps integrate it out. So have a joint model and then look at the marginal distribution of the bit that's left. And yeah, we've done a fair bit of work comparing these two, and they're not exactly the same. If the variability isn't huge, they're quite similar. So if you have, it's a little bit like where you have a Laplace approximation for if you have a Bayesian problem, you've got the posterior and you have a Laplace approximation. That is a bit like the doing the marginal versus the conditional approaches here. So yeah, I think you have to actually go quite a long way away from that in order for things to start to be different. And if they are different, then you would need to question whether either of them are okay. So yeah, no, I think it's an important point. But there's a rather large set of applications where taking an optimization approach to registration and perhaps doing it properly in a Bayesian way, integrating out registration, they're so similar that you can hardly tell the difference. So, but it's an important point, yeah.
Are there other questions? Well, if not, then let's
Good.
try again.
Thank you.